Welcome back to Calculus 2. Section 6.4, Working with Tayor Series. Our first application of the Tayor Series is the Binomial Series. We'll review notion of representing functions using the Tayor Series. We'll talk about the power series method for solving differential equations. And we'll end with a little trip into statistics. The first is the binomial series. Take a function f to be the binomial 1 plus x, quantity to a power r. Let's use the exponent r to be the integer values 0, 1, 2, 3, and 4. When you plug in an exponent r equaling 0, you have a base to a power 0, you get the constant 1. So when r is equal to 0, f is a constant of value 1. If we use r equaling 1, we'll get a linear function, simply the base to the power 1, or 1 plus x. If r is the power 2, we have the binomial of the power 2. From algebra, we know how to FOIL. 1 meets up with 1 in one way. 1 can meet up with x in two different ways, and x meets up with itself once. From algebra, notice that the coefficients being produced are from Pascal's triangle. As we read through row by row, we have a power 0 resulting in one term, power 1 resulting in two terms, power 2 resulting in three terms, so that the next row, power 3, would result in 4 terms. And the pattern is always the same, that you start with a constant and then you produce higher and higher powers on x. The question then is, what about the coefficients? And for that, we rely on Pascal's triangle, where if we start off on the left with a 0, add to 1, we get 1. Now start with 1, add 0, and get 1. Do that for the next row. Start on the left, 0, add with 1 to get 1. 1, add with 1 to get 2. 1, add with 0 to get 1. So in the next row, 0 and 1 will make 1. 1 and 2 will make 3. 2 and 1 will make 3. And 1 and 0 will make 1. 4 terms. Here they are. Pause and think, well, what about the next row? What are its coefficients? In the next row, that'll be for r equaling 4. We should have 5 terms and produce 5 different coefficients. So 0 and 1 make 1, 1 and 3 make 4, 3 and 3 make 6, 3 and 1 make 4, and 1 and 0 make 1. All right. Alternatively, instead of using Pascal's triangle, we have this binomial coefficient notation. One way to read this notation is r choose n. This notation r choose n may be evaluated using factorial notation, where we take the upper value, r, add a factorial to it, let that be the numerator. Look at the lower value, n, place that in the denominator as a factorial, and product it with the difference of the top value and the bottom value, quantity factorial. Nice? Now, what we've looked at is the power r being positive integers. And in this case, we have that the function f of x, defined as the binomial 1 plus x quantity to the r, may be expressed out in summation notation using the binomial coefficient. Good. Now, if this notation is not familiar to you, you want to play around with it a little bit. And one thing to notice is that r choose n by looking for a cancellation with the denominator may be expressed out in this form. To play around a little bit more, let's consider the case of r equaling 4. And using this notation, verify for a few of the coefficients that plugging in r equaling 4 and n taken to be 0, 1, 2, 3, or 4 will produce the appropriate coefficient. Do that again for r equaling 5 to come up with the function f. And then consider, well, what would you get for the function f evaluated at negative x? Nice. Okay, so we're comfortable with this idea of 1 plus x raised to the r, where r is a counting number, equivalently being represented using this summation notation. What we want to do is construct the Maclaurin series for this function f, where we're going to allow the exponent r to actually be anything whatsoever. Well, if we want to come up with a Maclaurin series, we're going to need to take derivatives. So if we look at this function, it's a pretty simple function. We have the chain rule at our disposal to be able to differentiate. Here's the 0th derivative, it's just the function. And the first derivative is bring down the power, decrement the power, and differentiate the base. Derivative of 1 plus x is just 1. Repeat. Second derivative, that power r minus 1 comes down, and the power r minus 1 is decremented. Third derivative, same notion. Now let's take a look here. We're stopping explicitly at the third derivative. And the coefficients, we have an r minus 1, and an r minus 2. Take a look at the amount that we're subtracting from r, the value 2. How does that relate with the derivative count? 2 is exactly 1 less than the derivative count. So if we wanted our derivative count to be n, then we would want to look at n minus 1 in order to come up with determining how many values do we subtract from r. But because we're subtracting that quantity from r, we need parentheses around the n minus 1. And then when we distribute the negative sign, we get n plus 1. And then on the power is simply the original power minus exactly the derivative count, so r minus n. All right, so this is taking derivatives. We know that a Maclaurin series is centered at a equals 0. That means we want to plug in for x equals 0. And when we plug in for x equals 0, we get a base of exactly 1 raised to a power is always going to be 1. In other words, we simply get the coefficients. And so that's what we can record here. And then because we want a Maclaurin series, we're really focusing in on the nth derivative at a, and that we have, recall from the assignment, this numerator quantity. But that what we want to write down are the nth coefficients, so we have to take the nth derivative at the center and divide by n factorial. Now, when we wrote down the binomial coefficient notation, that held for counting numbers r. And what we have here is an arbitrary real value r that happens to take an equivalent form to which the binomial coefficient may be expressed. So what we do is we make a definition. This quantity on the left is defined for counting values r. And here we're making a definition for this quantity on the right, which is perfectly well defined, to be represented by this left-hand side. And it's going to hold for any real number. Okay, so it's a fine point, but an important point. Good. Now with this definition, we can write down our f of x having a Maclaurin series, where it's a power series. We want the center to be at 0. It's a power series, so we begin the index at 0, and we need our coefficients Cn. And by what we just did, we've established that this notation is going to represent our coefficient. Good. And we name this series the binomial series. All right, well, what's something that we might want to know? Well, we would likely want to know what values of x can we plug in. In other words, what is the interval of convergence? How do we go about finding the interval of convergence? Good question. All right, let's look at this particular form of the binomial series. So we're just writing down the binomial coefficient. It can be expressed out in this fashion, and that we're using that notation to define the binomial series. And that with that notation, let's write out the very first few terms. That we're going to always start with 1 as the constant, and then add r. Remember that r is the power on the binomial, multiplying x, plus take that same r, but now decrement it by 1, and then place that over 2 factorial as a coefficient on x squared. Coefficient for x cubed is you use the same numerator, same denominator. You bump up the numerator with an r minus 2 factor, and you bump up the denominator by adding in a 3. And then you repeat that so that you're able to express out the nth coefficient as this notation, r choose n, on x to the n. Good. All right, so now that we have an explicit form for the binomial series, let's use this explicit form to investigate the radius of convergence, and for that, we look at the ratio test. So here is the nth term in the expansion. So to write down the n plus first term, denominator is going to become n plus 1 quantity factorial. This is the ratio test, so we want to introduce absolutes. Absolute on x raised to the n, add 1, absolute of x raised to the n plus 1. And then this numerator, well, it begins at r, and then it goes down until you've subtracted away n, and then you add 1 back in. So we know that we're going to replace out n for n plus 1. And then when we do that and distribute the minus sign, then we're going to end up with the 1's canceling, so that the last factor in the expansion is r minus n. Dividing by a sub n is multiplying by the reciprocal. And we come up with this expression. And there is a typo here. There is a factorial that's missing. So then with that factorial, we're going to end up with n plus 1 in the denominator. N plus 1 is in the denominator. For the x's, we see that we have n plus 1 copies of absolute x over n copies of absolute x, leaving us with 1 copy of absolute x. And then on the product of r's, r will cancel with r. That's going to happen all the way down until we come up with r minus n, add 1 back in, canceling out, so that r minus n has nothing to cancel out with in the denominator. This is occurring underneath absolutes, and thus we have the absolute of r minus n. As this is the ratio test, we want to let n tend out to infinity. And in the limit, we have the absolute of n over n is going to tend to 1, leaving us with absolute of x. So for convergence to occur, we need the absolute of x to be strictly less than 1. Nice. So this establishes the radius of convergence on the binomial series, and that it's the open interval from -1 to 1. Very good. Okay, so let's do an example. Let's construct the binomial series for this function f, defined as 1 over the radical of 1 plus x. Note that 1 plus x is taken as a radicand. Thus 1 plus x is being raised to the power r in the denominator. Or, overall, it's 1 plus x quantity to the r equal -1/2. So for this function f of x, we can find a power series to represent it. It will be a binomial series, since f is 1 plus x raised to the r equaling -1/2. And thus we can express it out as this binomial series. Recall that the binomial series begins at 1, and then you add in r times x. That's the linear term. The quadratic term is r product r minus 1 over 2 factorial, etc. Let's do that explicitly. So for our function f of x, it's 1 plus x quantity to the r equaling -1/2. And the very first term will be 1. Next, on the linear term, we're plugging in for r equaling -1/2, so we get -1/2 x. Likewise, plug in again. We'll have 2 factorial in the bottom. We'll have a quadratic x squared. Then the numerator will be -1/2, and then -1/2 minus 1 is -3/2. Nice. So in the next term, we're going to have the same numerator, but instead of a product of 2 terms, a product of 3 terms. And what's going to happen is that we're essentially adding in another -1. So instead of -3/2, we'll have a third factor, -5/2. Good. And then everything else is rather straightforward. And then that pattern continues on. Let's clean this up a little bit. So 1 is 1, -1/2 x is just itself, but here in the third and the fourth term, we can notice that there are a pair of 2's which can be brought down to the denominator, leaving us with a -1 times a -3, or 1 times 3. Note that we started with a positive term, went to a negative coefficient, and then come back to a positive coefficient. And then in the next term, because this numerator is a product of 3 negative terms, this will be a negative term. So we can see that it is alternating. Now, in this fourth term, the numerator has 3 2's, which may be brought into the denominator, so 2 to the power 3. And we'll explicitly write out the 1 times 3 times 5. And then that continues. Let's pause for a second and look at the pattern. This we wrote as 3. It's the same thing as 1 times 3. And this is occurring in the degree 2 term. If we take the degree 2 and multiply by 2, subtract 1, we get 3. Next term, we take the degree 3, multiply by 2, subtract 1, we get 5. So we can use that in our expansion of this numerator. That because we're taking these fractions multiplied, how many fractions do we have? We had 3, thus we get a 2 to the third. In the n plus first term, we're going to have n fractions in the top, which means that we can bring a 2 raised to the power n down into the bottom. What about the numerator? Well, it's going to expand out as 1 times the next odd number times the next odd number until you get out to 2n minus 1. Good. And then to alternate, we have -1 to the n. We just double check that. We know that we start at the 0th term, or the index being 0, and -1 to the 0 is positive, which matches up with this first term. -1 to the 1, that's the degree 1 term, would be a negative quantity. Nice. Okay, so we wanted to express out our f of x as a series, and here we've looked at the first few terms to try and figure out if there's a nice way to express out this quantity. And here we have the nth coefficient expressed out in a nice fashion, allowing us to then use summation notation. And since 1 is just 1, let's start the index at 1. So bring down the 1 and then begin the index at n equaling 1. And then we can use this notation. Very good. So, since the binomial series we saw earlier has convergence on the open interval -1 to 1, for the particular r value of -1/2, we came up with a nice expression. And we're setting it equal to this function f of x that's holding over the interval -1 to 1. Excellent. So here's an assignment. Use the binomial series that we explicitly wrote out and integrate. And then compare what you get with the given expression. And a second assignment, find the binomial series for 1 over binomial 1 plus x raised to the 3/2. And note that one way to go about it is, as we did in our example, looking term by term, but another way is, thanks to the absolute convergence, is to simply differentiate term by term. Fantastic. Something that we can do is use the binomial series to approximate a value. If we take 1 divided by the radical of 1.5, notice the radicand 1.5 is obtained when we let x equal 1/2. 1 plus 1/2 is the same thing as 1.5. We looked at how to express this right-hand side. Let's plug in x equaling 1/2 and write down the first 5 terms. 1 copies down. Let n equal 1. We'll have a minus value, have 1 over 2 to the 1, and then plug in x equals 1/2 to get another 1/2. Here's the n equal 2 term, the n equal 3 term, and the n equal 4 term. So this right-hand side is the 4th Maclaurin polynomial evaluated at 1/2. And it sums up to this given value. Well, how good is this given value at approximating the true value of 1 divided by the square root of 1.5? For that, we can turn to Taylor's theorem and come up with an estimate on the remainder. So we need to look at the 5th derivative of the function in order to estimate the remainder produced by the 4th Maclaurin polynomial. 5 derivatives on this function leads to this expression as a function of x. Since we are interested, by Taylor's theorem, at all values x between the center 0 and the point at which we are evaluating 1/2, and that input x appears in the denominator, to maximize this quantity, we would take the smallest possible x. That smallest possible x would be 0. Thus, for x's taken over the interval 0 to a half, this quantity is no bigger than 945 divided by 2 to the 5th. Okay, let's bring this together. We look at Taylor's theorem. Taylor's theorem says that the fourth remainder at 1/2 is exactly equal to this fifth derivative at some c in between 0 and a half divided by 5 factorial times the value x raised to the fifth, this value x. Nice. And then by this estimate that we came up with, we're going to swap out the fifth derivative at c by 945 divided by 32. And then we come up with the remainder is estimated by 0.00769. Nice. So, your turn. Repeat what we just did, but now go out to the fifth Maclaurin polynomial, evaluate that at 1/4, and then that is going to be a value that will estimate 2 divided by radical 5. And then use Taylor's theorem. You'll have to update your estimate on the sixth derivative over the interval 0 to 1/4 to come up with an estimate on how good p sub 5 at 1/4 does at approximating 2 divided by radical 5. Nice. Let's look at a graph real quick. We have a blue plot and a red plot. The blue plot is 1 over 1 plus the radical of 1 plus x, in other words, the function, and the red plot is the red curve. You see that over the interval of convergence from -1 to 1, the two curves are rather close, and that we, in our example, considered evaluation at 0.5. On this scaling, the red and blue curves are not far at all. And we did a computation for how close, in fact, the estimate is. You do the same thing, come up with a plot, but look for the function radical 1 over x and plot it versus its fourth degree Maclaurin polynomial. Nice. Well, that is the binomial series. And then let's go back and review how we had different functions. So this is table 6.1 taken directly from our textbook, where we have 3 different columns. Column of functions, their Maclaurin series representation, and the interval on which it is valid. Knowing these elementary representations, we can produce further representations. We can take the Maclaurin representation of cosine and plug in for x, radical x, to get the Maclaurin series for cosine of radical x. Note that this is really nice in the sense that x under a radical is the same thing as x to the 1/2. Cosine being an even function, we're taking only even powers of x. Now we're taking even powers of x to the 1/2. And so the Maclaurin series for cosine of radical x involves all powers of x. Nice. So go ahead and play around with that. For these different functions f of x, use table 6.1 to produce new Maclaurin series. Excellent. We have, in previous videos, discussed differential equations. Here in Chapter 6, we've been doing power series, and a lot of it is dealing with representing functions as a power series. Suppose that the solution we desire to a differential equation actually has a power series representation. Well, that turns out to actually be quite powerful. Let's see how. Let's use this initial value problem. Y prime is the unknown function, subject to the condition that the unknown function at time t equals 0 has some value. All right. So if we want to use the method of power series, then we're going to assume that the unknown function actually has a power series. So write that out. Y is given by a power series. As we're doing a differential equation, let's write out the explicit version. Let's take it to be the Maclaurin series, so we're going to center it 0. Now, in the differential equation, we also have not just the unknown, but the derivative of the unknown. We've made the assumption that the unknown has a Maclaurin series representation. Let's see what the Maclaurin series representation for the derivative is. Thanks to absolute convergence, we're able to differentiate term by term. On the left-hand side, we can apply a prime to come up with the new left-hand side, y prime. And on the right-hand side, again, thanks to absolute convergence, we can differentiate term by term. C0 is a constant, so under derivative, it goes away. C1 of x, if we're differentiating with respect to independent variable x, becomes constant C1. C2 on x squared becomes, under derivative, 2C2 as a new coefficient on linear x, and so forth. Not bad. Now go back to the differential equation and note that the derivative of the unknown is exactly the unknown. Well, that means that y must be y prime, but it also means that this right-hand side must be this right-hand side. Well, we can take that one step further and we can say that corresponding coefficients must match. Therefore, we can write down that C0 must be C1. But equally, we can write down that C1 must be twice C2, as well as C2 must be 3C3. And we can get infinitely many more such equations. Let's then jump to the initial condition and see what else we can pry out. Well, the function itself at 0 means that we can look at the Maclaurin series representation, and if we want to evaluate the unknown function at 0, that would mean plugging in 0 for x. Thus, all of these terms on the right-hand side will all go away, except for the constant C0. Thus, C0 must take the value k. However, from the differential equation y prime equal y, we also know that C0 must be C1. That is very good information. Record that. And then bootstrap that up into the next equation. We have the coefficient C0, and we also have the linear coefficient C1. Now let's find information on the quadratic coefficient C2. So let's solve for C2 to get that to be C1 over 2, or in other words, k over 2, by plugging in the previous line. Same story in the next line. Now that we have the quadratic coefficient, let's find the cubic coefficient. The cubic coefficient will be the quadratic coefficient divided by 3. But the quadratic coefficient is k over 2. K over 2 divided by 3 will yield k over 3 factorial. Note that there is a pattern here of k over 1 factorial, k over 2 factorial, k over 3 factorial, so that the nth coefficient will be k over n factorial. Well, that then solves the problem. Knowing the nth coefficient means we know the Maclaurin series. K is a constant appearing on every term by properties of series. Convergent series, we can bring the k to the front and write it down as x to the n over n factorial. Do you recognize this power series? Thumbs up if you do. Excellent. Here is one for you to play with. Use this power series method to solve the initial value problem. Y prime is k times the unknown, subject to the initial condition that y at 0, hint, you'll use again a Maclaurin series, is some value. Have fun. Excellent. The last thing that we'll do in working with Tayor series is consider statistics. Let's read this. If data is normally distributed, means it follows a Gaussian, i.e. a bell curve, with mean mu, that's the average, and standard deviation sigma, that's how much it tends to vary away from the average, then the probability that a randomly chosen value lies between some value and another value is given by a definite integral. Now, the definite integral has some constant that it's multiplied by. Note that the constant depends on the standard deviation, and then this curious constant, radical 2 pi. The integrand is an exponential, where in the power on the exponential, we're taking the variable of integration x and horizontally translating it, and then taking that difference and squaring it. So this is essentially e to the negative x squared. All right, let's bring in a nice picture. Normally distributed means that it's a bell-shaped curve. Another way to phrase that is that it's a Gaussian curve. When we look at a definite integral, we know that we can associate a definite integral with area under the curve. This is a definite integral from a to b. So pick some a value, pick some b value, and then shade under the curve. Excellent. Well, when you look at this integrand, that's e to the negative x, essentially, that is a rather difficult integral to evaluate. How can we go about doing that? Well, we can actually use power series to represent the integrand. Let's take a look at that. First, before we get into that, here's a nice assignment. If we use this notion that the definite integral is the area under the curve, but that in a probability setting, it can be interpreted as the probability that a randomly picked value from a set of data will take a value between, for example, 2 and 4. Well, if you use one of the values, a or b, and let's suppose that we take a to be the average value, mu, and then we let b go out to infinity, again, come back to this curve. So if we take a to be the average value, that would be here, and then we let b tend out to infinity, then what would this value be? And the hint is that this needs to be a probability. Okay. So looking back at the exponential function, we know that it has a Maclaurin series representation, thus coming up with a Maclaurin series representation of E composed with negative x squared is straightforward. This has absolute convergence. It has absolute convergence everywhere. Thus, taking this as an integrand, thanks to absolute convergence, we can integrate term by term each of these summands. And then by truncating, by only taking the first few, we come up with an approximation. Taylor's theorem allows us to come up with estimates on how good that approximation is. And so we can get an estimate to whatever standard we like. Okay, so here's that idea. We have the function, its Maclaurin series representation, its explicit form, then throw on integrals to all of this. Well, we actually want to apply this. That means that we're not looking just for indefinite integrals, which if we evaluate on the right-hand side, get rid of them all, we'll pick up a constant of integration. But we want to actually produce a finite value. That means we want to take an indefinite and turn it into a definite. But by the fundamental theorem of calculus, that just means evaluate at top, subtract evaluation at the bottom. Evaluation at top means that all the x's go to 1, and evaluation at the bottom means that everything goes away. Well, this difficult integral, which you throw your hands up if you're just using analytical calculus, you don't know what to do. Using this power series representation, you have this right-hand side where you can just take the first few terms to come up with a good enough approximation and call it a day. Well, can you call it a day? It needs to be good enough. What does that mean? We need to come up with an estimate. What are you going to estimate? You estimate the remainder. Well, remember that in an alternating series, the estimate on the remainder is super easy. To estimate the remainder, you just look at the next term. We can use that here since this series on the right-hand side is an alternating series. Thus, if we take just the first 5 terms, in other words, S4, come up with a value, look at the remainder, that means look at the 6th term, 1 over 10 times 5 factorial, and that is rather small. Good. So you give it a try. Suppose that we're looking at Australian males having some given height in centimeters with a standard deviation, sigma. And then you pick Australian male at random. What would be the probability that that Australian male would be of height between 160 centimeters and 170 centimeters? Well, that means evaluating this definite integral. What you want to do is make u subs to bring back this definite integral in the form that we were looking at in our example, and plug away. Nice. And then finally, come up with the estimate on the error to give an indication of how good a value this P sub 4 is. Very nice. So that's the end of this video. Thank you so much for watching. Please like if the information is useful, and I will see you on the next one.